Okay, great. So again, Calc 2 is building on our material for Calc 1, and Calc 1, the biggest ideas were the question of derivatives and integrals and the connection between them. So we have to start with the definition of a derivative. And first of all, we have a little bit of notation here. So we have three different pieces of notation. Right, when we're talking about a derivative, we either can say f prime of x. This is sort of the easiest one. This is the one that I'll typically use. But we also have df dx, and then we also have d dx of f of x. So three different notations for the derivative. And these are telling us any number of things, right? These are telling us, sort of the classic way to say it is the instantaneous rate of change of the function f with respect to x. But we can also say it is the slope of the tangent line. That's a more geometric interpretation. Or we can say the sensitivity of our function to change as x changes. So here we have a picture of a function, and we have a very geometric interpretation of the derivative at a point P. And we have a bunch of different lines here. You can notice we're really talking here about the derivative at this point P of the function f. So we're really talking about f prime of p here. And using these interpretations up here, we can see that the slope of the tangent line, so here's p, the slope of the tangent line seems to be this flat line right here. Maybe I should say the tangent line seems to be this flat line right here. And so the slope of the tangent line is the slope of a flat line. That's just 0, right? So that's the slope of a flat line. But we are also thinking of this as the instantaneous rate of change of our function. So at that moment, at P, our function is not changing its height instantaneously. And we can also see it as the sensitivity of our function as we change x. So as we change x a tiny bit, our function is not really changing at all. Now, the way that we constructed this, or the way that we interpreted this, was as follows, right? We thought about average rates of change, or we thought about a rate of change over a small average amount of time as designated by these lines here. That's not a straight line, as designated by something like this, right? Like this line right here. Notice from the point P to the point Q, a certain amount of time has elapsed, right? So a certain amount of time has elapsed, perhaps that looks to be about 1.5 seconds. And our function has changed a certain amount of height, right? Our function has changed from a height of 2 up to a height of just a little bit over 3. Right, so we call this down here, this was a change in time or a change in x value. And over here, we had a change in height or a change in y value. And so we can think about, right, that is over this window of time, this change in x. But we can imagine if we're trying to understand the instantaneous change, how our function is changing instantaneously, we can imagine taking a similar change, but over a smaller window of time, or an even smaller window of time. And by making our window of time smaller and smaller and smaller, we can begin to understand that our change in y, again, becomes smaller and smaller and smaller. And to understand the rate of change, so maybe I'll add one additional piece of notation here, this change in y, we can call this delta y. This change in x, we can call this delta x, right? Just notation indicating that there's a certain length here, a certain distance that has changed. And we can talk about the rate of change, right? That's a ratio here, rate of change, delta y over delta x. as the window of time, AKA, I'll actually write window of time, but AKA delta x itself, gets small, right? And as it gets small, it begins to better approximate that instantaneous change. And so what we see is that if we don't take this large, relatively large change in x that we have down here, if we instead take points that are closer and closer and closer to our point P, the slope of that line gets flatter and flatter and flatter. And what we see then is that this instantaneous rate of change is 0. So this was a conceptual understanding of the derivative. But of course, there are some hard and fast rules that are associated with the derivative as well, these computational rules that you're asked to understand. And we have a bunch of those rules that I want to talk about. And I want to remind you what those are. For better or worse, this will just become a bit of a list, a bit of a slog, but I do want to make sure that we all sort of understand and appreciate each of these rules. The first four, the sort of four up top, are our most basic rules, talking about any function. Here we have d dx of a constant function. Again, we're reading that as the derivative of a constant function. And the derivative of a constant function in this case is just 0. The rate of change of a constant is 0. A constant doesn't change. The rate of change of two functions added together, so the derivative of f of x plus g of x, this will be the derivative of the first, so I'll just say f prime, plus the derivative of the second. The derivative of a difference is going to be exactly the same, so the derivative of f minus g is just f prime minus g prime. And the derivative of, we can interpret this as a constant times f of x. That's a constant times a function. Well, that is going to equal a constant times the derivative of the function. So c times f prime of x. Right, so we have these as our basic building block rules of taking derivatives. Additionally, we have three, I'll call them more complicated rules. These are, well, I'll call them more complicated because they are more complicated. These rules are absolutely more challenging. I suspect you've seen them a number of times, but maybe over the break, or if it's been a little while since you've seen calculus, these have become a little bit fuzzy. And so I would encourage you to go back and double check these, make sure that you can use them in a variety of situations, as we'll do here in a moment. But we have the product rule, which tells us how we take the derivative of the product of two functions. So f times g, that's going to be, so the derivative of f times g, we're going to take the derivative of one of these functions times the other, plus, and then we're going to do the same thing with the rules reversed. So f prime times g plus f times g prime, or the derivative of the first times the second plus the derivative of the second times the first. The quotient rule is even weirder. I'm just going to write this one out. So this is the derivative of a quotient of two functions, f over g. And that's going to be the bottom time, let's fix that. That's going to be the bottom times the derivative of the top minus the top times the derivative of the bottom, all divided by that bottom function squared. Oof. Yeah, so that one's a mouthful. And then the final rule, the chain rule, right? Those of you who saw my introduction saw that I love the chain rule. The chain rule is one of my favorite rules, but it's also by far the most complicated of them in actual applications. So when we have a composition of functions, f of g of x. So we're taking the function g, we're plugging it into the function f, we get this composition, and when we go to take its derivative, we get the relatively complicated f prime of g of x times, at the end, g prime of x. So I don't actually know why this is called the chain rule, but I always think of it as sort of like a chain lightning situation. So like the lightning, the derivative first hits the outer function f, we get f prime of g, and then chain lightning style, the derivative also hits the g. So at the end, we multiply by a g prime. That is, I learned the chain rule 10 or 15 years ago. That is the justification I came up with myself that day. That's what I've been telling myself ever since. That's what I tell you all. Okay, I love it. So keeping these rules up here for a moment and pivoting back to item pool, I want to ask you all to think about the following question, which should appear on your device. What is the correct way to differentiate the function that's shown here? Not only what is it, but also what is the correct rule or set of rules to use? And I'll flash this back up here for you. Take a moment to just think through that. Okay, we've got some answers coming in, which is great. You might have to reload your device. That's what I had to do on my phone. Okay, so we've got a bunch of answers. It looks like most of them are consolidating around one of these. Let's finish and reveal. So because the way this was written was sine of x times x cubed, you're absolutely right. This was a product of two functions, the sine function and x cubed. So of course this required the product rule. And then it looks like there was some potential wrong answer with which way we use the product rule. As a reminder then, the product rule, once we knew we had to use it, we would end up with these two different terms, f prime times g plus g prime times f. So we would end up with two terms, and each of them, the derivative would hit once. So we would end up with the derivative of sine times x cubed plus the derivative of x cubed times sine. Okay, I love it. That occurs to me that we actually need to talk about the derivatives of these functions. I might have flashed that question a little bit too soon, right? What is the derivative of x cubed? What is the derivative of sine? You identified that it required a product rule, but maybe we couldn't remember what those derivatives were. So what we have here are a bunch of our basic functions, which in this class we're calling modeling functions because this is applied multivariable calculus, and these functions are often used to model real-world phenomena. And the question is, what are each of these derivatives? Well, first of all, our most important modeling function is just the straight line, right? Y equals mx plus b, or f of x equals mx plus b. The derivative of that is just going to be the constant m. So the derivative of mx plus b is just m. The derivative of the polynomial expression x to the n, right? This is a power function, and so we use the power rule. That became n times x to the n minus 1. So our polynomial functions follow this power rule. Our exponential functions, right, follow a different rule. So that's if our x value is in the exponent. And what we see there is that our e to the x, the derivative of e to the x is just e to the x again, while the derivative of a more complicated a to the x, where here A is any constant number. Let's say any constant that's greater than 0, right? So think 2 to the x, 3 to the x, you know, e to the x, but maybe not e to the x. Its derivative is a to the x times an additional constant, the ln of a. I guess the derivative of the natural log function, the derivative of ln of x, is just 1 over x. And then our two most important trig functions, we've got the derivative of sine, amazingly enough, is cosine. And the derivative of cosine, frustratingly, it's not sine, it's negative sine. Okay, so those are our those are our 7 major derivatives of modeling functions. Okay, so with that in mind, right? Again, I told you we'd end up just having to list a bunch of these. We have gigantic list of rules for derivatives of modeling functions, specific modeling functions, and also overall derivative rules that apply to any function whatsoever. The joy of taking derivatives is that we can use all of these together, potentially in interesting ways, to take the derivative of just about anything. And we see 4 examples down here. So I'm going to ask you to take about 5 minutes to compute as many of these derivatives as you can, as carefully as you can. And I'm opening up an item pool question for you, simply asking you which one or which ones are you least confident in. So take a couple minutes. You don't have to get them all. You don't even have to get them all right. Just attempt each one and then see how you are feeling about them and which ones you are less than confident in. want to give you about 1 more minute to finish up what you can, with again the understanding that I'm not giving you a ton of time, and if you don't finish them all, that is a-okay. But I am asking you to vote on the ones that you feel least confident about. You can vote on multiple if you're feeling less than confident about multiple. And I'm going to write up what I believe the correct answers are for each of these, just to make sure that they are recorded somewhere. Okay, we have a couple answers up here. Let's see how everybody's feeling item pool style. We've got a bunch of votes, and it looks like things are split pretty equally between D and C, with B being a follow-up question as well. Okay, great. B is being, all right, let's talk about these. C and D at least, for sure. So, focusing in on C for a moment, I want to say that the main challenge in C is coming from the application of the quotient rule, right? The quotient rule was our, the one that looked the most bizarre at the outset. We have a quotient here with a numerator and a denominator. And so when I see this giant quotient, I think that I'm going to need to use the quotient rule. And so I take, again, the quotient rule was the bottom times the derivative of the top. And we see that's exactly what we have going on here. The bottom times the derivative of the top. And then minus the top here times the derivative of the bottom. And again, the derivative of e to the x is just e to the x again. All divided by the bottom squared. So that's just e to the x, put it in parentheses, and square it. A great question here, anticipating your question, a great question here is a question of how much we need to simplify, right? Do you have to cancel things out? Do you have to rewrite this in a nicer looking form? No, I do not care. By sort of getting to this answer, you have done the act of taking the derivative. If you want to simplify it, I say go for it, but I'm telling you up front, I really won't care. That's me personally. I won't care about whether or not you simplify this down to some ideal form. And then D was also voted on. D is an application of the chain rule. So I do wanna, let's take a moment to talk about D as a chain rule problem. So I'll actually, what's the best way to do this? I'm gonna zoom in nice and far, and then we'll talk about e to the 5 plus x squared plus cosine of x. So when I see this problem, I internalize this as follows. I think this is e raised to the, and then here I see a second function. I think of this as having secretly a couple of parentheses around it, right? This is e raised to a function, and this is exactly what we mean when we say a composition of functions. I've taken the weird function 5 plus x squared plus cosine, and I've plugged it into the exponential function. So this is e raised to all of that. what that gives me then is when I take that, when I want to take the derivative, the chain rule says, you know, chain lightning style, that, let me write this off to the side. The chain rule says that the derivative of f of g of x, so that composition of functions, the derivative of that is equal to, first we take the derivative of the outermost function, leaving the inside function the same, and then we multiply by the derivative of the inside function. So in this case, the outside function is the exponential function, e to the x, and the derivative of e to the x is just e to the x. So the derivative of this, right, the derivative of this is going to be, we applied the derivative to the outside exponential function. It stays the same, so it's still e to the inside, 5 plus x squared plus cosine, and then times, chain lightning, that derivative of the inside, so times the derivative of 5 plus x squared plus cosine. So that just becomes, because those are all being added together, the derivative of 5 plus the derivative of x squared, 2x, plus the derivative of cosine, which is negative sine. All right, so that's how I would, you know, not only how we get the answer, but how I would approach that problem. I'm going to skip over problem B for now. There we go. Skip over problem B, but I want to encourage you to double back and check your answer to B and make sure that you feel confident in this answer. Specifically, I would highlight that this is a product, right? There's the cosine piece times the sine piece. But when you go to take the derivative of each individual piece, this isn't just cosine of x, this is cosine of 5x, sine of 4x. And so there's something challenging happening here. I would say double check and make sure that you're happy with that answer. And if not, this is something that we can talk about in office hours or something that we can talk about in class next time. All right, with our final 13 minutes, I want to pivot to integration, the opposite of differentiation. Oh, I shouldn't say that yet. Integration, an interesting thing that we'll talk about now. Integration, right, is a measurement of area, and it's typically identified using this definite integral, right? So the definite integral has this notation here. I'll actually zoom in on this in a second. Okay, so this is our definite integral. It's using this notation, and it's measuring the accumulation of area under the function little f of x over the interval a to b. So specifically, if this was our function f of x right here, then this object up here is measuring the total amount of area that we see right here. So that's our definite integral. It is just a tiny bit more complicated than that because we include these two additional words, directed and signed. So it's area, but it is directed and signed area on our graph. When I say it's directed, what I really mean, let me use two different colors to underline that. So when I say it's directed, what I mean by that is that if I take the integral from a number a to a number b, the order in which I write these matters. This is going from a up and to the right to get to b. And if I were to flip those numbers, I would end up with a negative integral, sort of by convention. In other words, when I talk about directed, by convention, my integral should be written so that the lower number is smaller than the upper number in these numbers A and B, these bounds of integration. And if I flip them, I introduce this additional negative sign. So the reason that we call it signed area, that is because the area is only considered positive if it's above the x-axis, considered negative if below the x-axis. And so as a quick example, even without knowing how to compute integrals or having anything memorized, just understanding this idea of signed area, we could compute, if we wanted, the integral from 0 to 2 pi, the definite integral from 0 to 2 pi of the function sine of x dx. Take a moment, don't say anything out loud, but take a moment and think about what that might be. As a hint, here's a graph of sine using my best attempt at artistry. There's function sine. This is from 0. This is pi. This is 2 pi. So when we talk about signed area, then we see that all of this area right here, that's going to be positive area. It's above the x-axis. And then all of this area over here, right, that's going to be negative area. That's below the x-axis. And so if you were thinking that maybe the integral from 0 to 2 pi is actually 0, you'd be completely correct. Computing nothing and just understanding that the integral is measuring signed area, we see that this is a positive amount of area and it has an equal negative amount of area just by the symmetry of the sine function. And so in fact, this total area sums up to be 0. The positive area and the negative area exactly cancel each other out. No computation necessary. So that is our definite integral. Of course, we can compute definite integrals, and we will compute them before this class is up. We also have an indefinite integral, right? Also called an antiderivative. So there's some potentially very confusing language here between definite integral and indefinite integral. And we say that the indefinite integral is simply an antiderivative. It is a function whose derivative is the function f in question. And we write it as follows. So we say, use the same notation, the same long squiggle of little f of x, and we call that the indefinite integral or the antiderivative of little f of x. So I wanna address the fact that this is really confusing notation, because it is confusing notation. There are two objects here, the definite integral and the indefinite integral. They look almost identical. You know, they sound identical when I say them out loud, but they're describing two different things, right? So I'll sort of write what is basically up here, but in sort of a condensed version to emphasize it. The definite integral is an object that looks like this, and it is measuring signed directed area. I'm just gonna, directed signed area. And we can compare that to the indefinite integral, which is this object that looks almost the same, except we're not using bounds of integration. We're not writing it with a to b. And this is not a measurement of area, right? This is an antiderivative. It's representing a function whose derivative is the function f of x. So that's extremely weird, and that's extremely confusing that we're using such identical notation to describe two different objects. And the reason that we use this is because those two different objects are secretly deeply connected, and in fact, sort of two different aspects of the same idea. And that is what's given to us in the fundamental theorem. Get a quick drink of water here.
Dr. Ross.
Yep.
I had a question. If you go back up about the, you flipped the A and B on the other integral and said direct. Yeah, I was just confused about this part.
Okay. So the question was about this the statement of it being directed. It's possible you haven't seen this previously in Calc 1. That's A-okay. Maybe I should have said this in a slightly less confusing way. What I really mean here is that by convention, we'll always write a definite integral that we're interested in by writing the smaller number below and the larger number above. So when I say directed, I guess I'm going to say that these bounds of integration matter and the order in which we write them matter. So if I was interested in understanding the area under the function x squared between 0 and 2, I would write this. And if I ever see, if it ever pops up in an equation, that I have something like this, right? I would say that these two things are not equal to each other. But in fact, if I were to see something like this, I would interpret it as being this original object with a negative sign. So again, I think I said that more confusingly than it needed to be said. What I should really say is if you see something like this, where the order is not correct, just flip them and throw on a negative sign, right? It's indicating the negative of the actual area, the actual integral. That's all I meant by that.
Thank you.
All right. Keeping an eye on the time and with a strong desire to both let you out on time and also fill in at least the rest of this page, I want to highlight sort of the first fundamental theorem and the second fundamental theorem of calculus, which helps us better understand the relationship between the definite and indefinite integrals. So here we're going to say, the first fundamental theorem of calculus can be read as follows. If we take a definite integral of our function, we can say the definite integral from a to t of f of x dx. This is a definite integral. I'm going to run out of room there. That is a definite integral. It's a definite integral that depends on t. In the sense that if I plug in a different number t, I get out a different definite integral with a different number. And as a result, this is a function, right? This object is a function of time, or a function of t. This is a function of t, a new function, measuring the accumulation of little f. So the first fundamental theorem of calculus says that if this new function, which we'll call a of t, right, the accumulation of the other function, what we're claiming here is that a of t is an antiderivative of f of x. And so therefore, the derivative of a of t, aka the derivative of this definite integral, is just going to be the function little f of t. In other words, if we create our accumulation, our integration as a function, right, if we introduce this a of t, then it can be undone with differentiation. So in other words, differentiation, I'll just say derivatives, undoes or derivatives undo integration. Right? And one way that we can think about this is we had our function f, we set up an integral of it, we took the derivative of that integral, and we found our f of t again. We found we rediscovered our function f. The second fundamental theorem of calculus is the same statement or a similar statement that's said in the reverse order. So if little f is a smooth function and capital F is any antiderivative of little f, then the integral from a to b of f of x, notice again, this is a definite integral. I could rewrite this, and it feels a little unnecessary here, but I can rewrite this as the integral from a to b of capital F prime of x dx. Right? Again, if capital F is an antiderivative of little f, then little f is the derivative of capital F. And so little f is just equal to big F prime. And so this will be, we can write it in this form, capital F of x evaluated at A and at B, which is interpreted as capital F of B minus capital F of A. And this version of the fundamental theorem is the one that you're most likely to remember from last semester. It's the one that's used most often. It is written in a more concise way as the integral from a to b of little f of x dx equals capital F of b minus capital F of a. You know, if you had a page in your notes and you had a formula boxed, this was probably the formula that was boxed. But again, we can think of this as follows. If we take a capital F, we take its derivative, and then we take a definite integral of it, we recover our capital F evaluated at these appropriate endpoints. So in other words, integration or integrals undo differentiation. And so though we haven't explicitly calculated any definite or indefinite integrals yet this semester, we can see based on the fundamental theorem that they are intimately connected to these derivatives. Okay, and keeping an eye on the time, I think that has got to be where we stop things for today. So I'm going to stop the recording.